Good afternoon, everyone. My name is Ruben Munera. I come from the University of Antioquia in Medellin, Colombia. First, you might notice that the title that I have here is not the same that we have in the program. And I just put it there because I wanted to show you like the big picture, like what is it that we want to achieve with everything that we're doing. And what we want to do at the end is to find a strategy to produce omega-3 fatty acids in front of the problem we have with malnutrition with our children. Being a developing country, we face a lot of problems, and malnutrition in children is one of them. Okay? So, what I will talk about today is one of the first stages that we need to do in order to reach our final goal, and is that we have to find a way to determine the polyunsaturated fatty acid content in microalgae. In this moment, what we are doing is that we are working with a microorganism that is called Schizophytron nemasino. I will talk about it a little bit more further on, and we just needed to find a way to see how much like omega-3 fatty acids were in there. So that's what I will be talking about today. So why omega-3 fatty acids? Why DHA? Because it doesn't say omega-3 fatty acids, it says DHA. Well, when we talk about omega-3 fatty acids, there are like two main compounds that we need to take into consideration, like the docosahexaenoic acid, which is a 22 long chain of carbon, and eicosapentaenoic acid. I'm just like making a little bit of publicity on this one because this is the one that you find in labels. I don't know if you ever saw like a can of formula for babies. They always have like DHA very big in it. Yeah? Why? Because DHA is very important when it comes to the development of children. You know, we want to have like happy children. We want to have children that have good eyes and good brain. So that's why we're doing that. And also, like omega-3 fatty acids and DHA in particular have been linked to preventing circulatory system diseases. Yeah, so it's not only good for children, but it's good for everyone. Okay, so that's what we want to know. So usually we talk about, okay, we need to take omega-3 fatty acids. We need to have this nutrient in our diet. But how much? Yeah, we don't know. So I asked the question. This is a question that I actually ask people around. And they ask me, okay, what do you do? I said, do you know how much omega-3 you are consuming every day? Well, mostly the answer is no. We don't know how much we need to take. We don't know how much it's in our diet. And sadly, the answer is, you check this number here. This number is a ratio to omega-3 and omega-6 fatty acids. No? Omega-6 fatty acids are the ones that get like all the good publicity. You see it on the commercials, yeah. You see on the butter, you see on the oils that we consider that this is good for your heart because it's got omega-6. So in our diets, Western diets mostly, we have some studies have said we have 15 units of omega-6 fatty acids against omega-3 fatty acids being 1. But this is way too high. The recommended for having all these benefits would be like 4 to 1 maximum. Okay? So our diets are far away from this optimal condition. So we need to find new ways. And why is that? Why do we consume this? Why are we not close to this? Yeah, well, there are many reasons. Usually omega-3 fatty acids are mainly used in fish, blue fish, which sort of like tuna, mackerel, salmon. We don't eat that all the time. Yeah, like maybe in special occasions. That's the 15 to 1 maybe. So getting to this is like really important. So it's like, okay, we want to measure lipids. We want to produce lipids. But how are we going to produce these lipids? So what we're going to do, or what we thought about doing, was using our little friend here. It's called Schizophytrum limacinum. And Schizophytrum limacinum is this microalgae that was, like, let's say, discovered about 30 years ago in the mangroves of the Pacific Islands. And they have an amazing capability of producing omega-3 fatty acids. They are really good at doing that. So we are trying to take that ability that they have and take advantage for the necessities we have. So we needed to know how to quantify this amount of lipids they are producing. Because now what we know is they produce a lot. You see them. This is an actual picture of a culture under the microscope. Yeah, this would be our little fellows. But then we needed to develop an easy to apply and feasible method for measuring content in Schizophytrum limacinum. Okay, so that was basically what we needed to do in our early stages. So the first thing we did, what we usually do, we ran a bibliography search. Don't work for me. A bibliography search, and we found usually we have like gravimetric methods, we have dyeing or staining methods, yeah, and they all have like pros and cons. So first, we try to go with the gravimetric methods because they are widely reported, widely used, but we came across some problems. What problems we found? Well, basically, they need like really, really big samples. And we don't have those samples because in this moment we're working like at a laboratory scale, we have small vials, and we are getting like little amounts of oil. So we needed to wait, to do like 1, 2, 3 runs so we can have like a decent amount of oil so we can measure using gravimetric methods. And then we couldn't like be able to tell the difference, like which culture was the best, because what we were doing was just putting it all together in one pile so we can do the measure using the gravimetric method. And on top of that, these methods tend to be like quite lengthy. They require a lot of steps, and they require a lot of time. So we said, okay, we need to do something different. We need to look for another solution. So we came across these staining dye methods, which tend to be quite faster, much faster than gravimetric methods. And also, they tend to be like, they tend to use really small amounts of samples. So what we can find, or what we found actually was, we found there was like a commercial kit ready to use, which is called Boripi. But being in a developing country, working at a public university, sometimes like money comes as a problem, yeah? And research is not as funded as it should be where we come from, but none the way we're trying to find ways around that. So what we did is that we tried and kept looking, and then we found this SPV, which is sulfur phosphorus vinyl, yeah? And it was like really good, it was really fast, you used like small amounts, but then we started to notice that they change over time. It was highly dependent on the profile of the lipids that we were measuring. So we couldn't get like a stable measure over time, so that was also a problem. So then we found the Nile red. Okay. And Nile red, even though it has been used for years past, yes, this is one of the, I don't know if it's one of the first methods that came across, but I know it's been like over 40 years being used. It actually worked very well for us. So what I'm gonna do today is I'm gonna tell you like what we did, yeah, and how we use it in order to successfully measure our lipid content with the drawbacks that we had at the time. So, how does the Nile red fluorescence work? Which is quite simple. This is nothing. We just need to have our Nile red. We need to have a solvent. And later, I'm going to tell you what happened with a solvent, not as easy as you might guess, because we need a carrier to go through the membrane in the cell wall. And then once we are inside the cell wall, where the carrier just leaves, and then we find our complex, which is a complex of the Nile red molecule, which is binds to the triglycerides inside the cell, because the DHA and the EPA come from triglyceride forms. They are stored as a way of preserving energy within the cell. That's what's going on. So they bind together, and then we can use that to measure how much we have. So then another search, and we started to, how do we use this method? Okay, and I told you that, okay, yeah, we need a solvent. But solvent, we found there were a lot of possibilities. We could use DMSO, we can use glycerol, we can use ethanol, acetone. So which one did we use? What was the best for us? What we did is we had dimethyl sulfoxide, which is this one. We had ethanol, we had acetone available in our lab. So we started seeing how the method would behave with all these three solvents. Okay. We also find some literature about how to use the Nile red, what was the optimal concentration of the cells, some incubation time, which is crazy, as low as 5 minutes, as much as 40 minutes. And this is highly dependent on the solvent that you are going to work with. So what I'm going to show you now is finally what we got. So we studied, as I said before, DMSO, acetone, ethanol, and we prepared our Nile red concentration, 1 microgram per milliliter, very, very small amounts, I mentioned before. And we found that after 10 minutes, there was no more changes in the fluorescence, so that was our incubation time. And also we tried different temperatures, and we set for 35 Celsius degrees. We think in Celsius degrees, so here is only thinking 95 Fahrenheit. That was our parameters. So analyzing these different solvents, there was a problem with acetone and ethanol because it wasn't stable. And in the samples that we have, because this allowed us to work at a scale of microplates. Now we're using microplates to run our experiments. And before we were using amounts of 10 millimeters, which was a lot. And it was really, really solvent consuming. So we are down now to the scale of microplates. But because we're working in this way, acetone and ethanol being really good solvents, but they are really volatile. So by the time we prepared the sample and the time we got to the equipment, it was gone. Not gone, but enough to have changes in time. Okay? So we found out that DMSO, dimethyl sulfoxide, was our best carrier, okay, based on those experiments that we did. So we chose to work with this one. After that, what we needed to find then was our excitation wavelength and our emission wavelength. The excitation is the optimum wavelength at which the complex absorbs the most amount of energy to be released afterwards. So what we did is, at a fixed concentration, we swept the different wavelengths, and then we find that the optimum wavelengths were 535 nanometers for excitation and 660 nanometers for emission. But on top of that, what we did, after we found these parameters, we wanted to compare it. And what we did is that we compared a commercial sample of omega-3 fatty acids, because we wanted to know how it would work. And we compare it to our oil from the schizopetrine damascenium oil. We wanted to see if, but not all commercial samples work. We had to find a commercial sample that had neutral fatty acids, because that's the ones that work with the method. So after we found one, we compared them, and we can see that there is virtually no difference in the behavior of our sample and the behavior, which is the orange one would be our sample and the green one would be the commercial sample. And so this was like really good for us, because we saw that what we were doing was on the right path. We were getting like, at least in this case, a good approximation to where we want to get at the end. So after we did that, we wanted to obtain, because at the end what we want to do is measure the liquid amount in a very fast way. We just created like our dilutions. We did some dilutions of the oil sample, and you can see the units are only like 100 microliters of the sample combined with 100 microliters of the Nile red fluorescence. And this, in the microplate, finally gave us this chart. So this is what we were looking for, an easy way to find, to measure our lipid production in terms of fluorescence. Now, I apologize, because I realized 2 minutes ago I didn't put names here, but this is concentration, micrograms, and this is random fluorescence unit. It's just like, now, this are important. Sorry to go back, because I forgot to mention. These are important because we found out that the method is linear only when we use very, very diluted samples, when the concentrations are extremely low. That's the only way the method will work. And we try to do this. Actually, searching for information, we saw some reports of people working with higher concentrations, but when we tried to replicate that at the laboratory, we never got a linear behavior. Further on, we found out that it was only linear in these at these small concentrations. So the relevance of the work for us, and I hope for you, is that as long as we don't have, because this is a question we ask ourselves, why don't we use an existing chart, a chart that we can already use? So we didn't find that there's any study that correlates like lipid production for any microorganism and fluorescence. So as far as we don't have that, we need to keep doing that for each and every single microorganism, because we don't know if it's going to be the same or if it is going to be different. So maybe there is something that we can study on in the future. We needed to check all the advantages and disadvantages of each and the single method that we use. And the minimization of sampling and the time saved was what we were actually looking for. So we concluded that yes, red Nile fluorescence, even though a classic method, is still good for us. So sometimes it's useful just to go in the drawer and see what's there, because we are only focused like in these new methods, but sometimes what's old is still good. And the determination of lipid content microalgae from Stichophytron dimoscinum can be done efficiently with precision using red Nile fluorescence. But, as it was mentioned, we need to be careful. So what we need to do is we need to repeat this every time that we want to work with a different strain. And we need to do that. We need to check the solvent that you're going to use. Those were like the two main points that we were looking into, and that we found out. We spent about 3 weeks trying to, no more, 3 weeks discussing, but previous work, discussing like, what is the problem? And then the problem was two simple things. You know, what solvent we were using, and that didn't work for the microorganisms that we had. the don'ts, so that you need to be very careful how you use the concentration when you want to do this. Yeah? So that's what I wanted to show you. Thank you very much for your time. If you have any questions, I will be more than happy to answer. That's my contact. Everyone I reach you.
If there are questions? Thank you so much for your story. And now we have the last oral presentation of today's session, the last but not the least. And Dr. Juan Martin Delgado Naranjo from Universidad de Antioquia, Medellin, Colombia, is invited to present effect of carbon to nitrogen ratio in the growth of Schizochytrium limaceum towards DHA reduction.